Have you ever noticed how we keep hearing about so-called 100-year weather events, but they seem to happen almost every other year now? Massive floods, record-breaking storms, wildfires bigger than ever before. The term 100-year event technically means there's just a 1% chance of it happening in any given year. But here's the problem. Researchers can't always be sure whether these events are actually rare or if the climate has shifted so much that they're simply part of our new normal. This is where some very exciting new research comes in. At the University of Washington, scientists have developed an artificial intelligence model that can simulate up to 1,000 years of our current climate in just one day. Imagine that something that used to take months of supercomputer time can now be done on a regular processor. In half a day, that's a massive leap forward for climate science. Traditionally, weather and climate forecasting relies on physics-based models running on huge, power-hungry supercomputers. These machines are expensive, they consume enormous amounts of energy, and even then, most models can only make accurate predictions about 10 days into the future. But climate science doesn't just need 10-day forecasts. We need to understand variability across seasons, decades, even centuries. Without that, we can't fully answer critical questions like, is this particular flood a freak event or a symptom of long-term climate change? The new AI model, called the Deep Learning Earth System Model, or DLESyM, tries to tackle exactly this. It's the work of a research team led by Professor Dale Doran and graduate student Nathaniel Cresswell Clay. What makes their model special is that it runs on a single processor, not a supercomputer, and yet it can simulate 1,000 years of climate variability in just 12 hours. For comparison, doing the same job with conventional methods would take around 90 days on one of the fastest computers in the world. So how is that even possible? Well, here's the clever part. The model was trained for short-term, one-day forecasts, but in the process it learned to capture seasonal and long-term climate variability as well. It actually uses two neural networks working together, one for the atmosphere and one for the ocean. The ocean model updates every 4 days, while the atmospheric model updates every 12 hours, reflecting the fact that oceans change more slowly than air. Together, they can mimic the complex interactions that drive our planet's climate. This design is pretty groundbreaking because traditional AI models in climate science struggled to capture those longer-term seasonal patterns. There just wasn't enough historical seasonal data to train them well. Remember, the most accurate global datasets for daily weather only go back to around 1979. That's enough to train a model to predict tomorrow's weather, but not enough to reliably understand seasonal cycles. By splitting the problem into atmospheric and ocean components, this model sidesteps that limitation. And it works surprisingly well. When researchers tested the model against leading physics-based supercomputer models, it actually performed just as well, and sometimes even better. For example, it was better at simulating tropical cyclones and the Indian summer monsoon. It also captured tricky atmospheric phenomena like blocking. That's when high-pressure ridges get stuck in place, keeping one region unusually hot and dry while diverting storms and rain elsewhere. Many traditional models don't do a great job with that, but this AI model did. Of course, it's not perfect. No model is. Neither the AI system nor the big supercomputer models can predict every detail with 100% accuracy. But the fact that this lightweight, energy-efficient AI approach is competitive at all is remarkable. Think about what that means. Instead of needing access to one of the world's top supercomputers, a graduate student or a smaller research lab could run complex climate simulations on an ordinary computer. That democratizes climate science. It means more people in more countries can study climate variability without waiting for limited supercomputer access. And here's another important angle: the carbon footprint. Running massive supercomputer simulations for months at a time consumes huge amounts of energy, which ironically adds to the same carbon problem researchers are studying. This new AI model, by contrast, has a much lower carbon footprint. It's faster, cheaper, and greener. The researchers also made the model open access, which means anyone can download it and experiment. That could speed up innovation dramatically, because instead of just a handful of institutions working on these problems, thousands of scientists around the world could contribute ideas, test scenarios, and improve the model. And the possibilities don't end here. Right now, the model includes the atmosphere and the oceans, but the team is working on adding more components of the Earth system, like land surfaces, vegetation, and soil. Traditionally, these relationships are so complex that researchers try to simplify them into equations, but AI can learn them directly from data that opens up the potential for much more realistic Earth system models in the future. So what's the big picture here? Well, if you care about the future of our climate, and we all should, this is a very hopeful development. With tools like this, we can run long-term simulations more easily and get better at answering those key questions. Is a given storm just bad luck, or is it part of a shifting climate baseline? Are heat waves like the ones we've seen recently a rare event, or are they becoming the new normal? Having more clarity on those issues isn't just about science, it's about preparedness. Governments, farmers, city planners, they all need accurate long-term forecasts to adapt and make smarter decisions. Think about it. If you live in a region prone to drought, wouldn't it be life-changing to know with much greater certainty how severe the coming season might be? Or if you manage coastal infrastructure, wouldn't you want the most accurate picture possible of future storm surges? This model brings us closer to making that a reality. So to sum it up, what these scientists have built is not just another climate model. It's a leap forward in how we approach forecasting faster, more accessible, and surprisingly accurate. And perhaps most importantly, it gives us a tool to understand whether the extreme weather events we're living through are flukes or warnings of a climate that has already shifted under our feet, and that I think is something worth paying attention to.